Hey folks, this is Captain Jones here to give you the first look at our data path for the LC-3 computer. Our objectives today are to identify the components that are in the LC-3 and describe their function, and then also describe the signals that control those components. So we'll start to sort of peel back the layer on this computer and see actually how it works. So recall from a previous lesson that this is our von Neumann model. This is kind of the basic framework that we're going to use to build out our LC-3 computer. We've got 5 components: memory, processing unit, input, output, and our control unit. I'm gonna rearrange this though slightly. It's sort of a stepping stone to get to our LC-3, and what I'm gonna do is show the processing unit, the memory, the input, the output being connected all to the same set of wires. In other words, the same bus, the processor bus. So hopefully you can look at these two side by side and know that. Aside from the fact that I've got a bus over here, they're effectively the same diagram. Okay. Now let's take a look at the actual LC-3. I'm going to put this diagram, this modified von Neumann diagram, to one side and show you this. Holy cow, there's a lot going on here. Bear with me. When I show you, hopefully we can start to see that these two pictures are somewhat similar. So you can see, for one, notably, I've got this processor bus in the middle of this block diagram here, and then this massive black line going all the way around my LC-3 computer. This is that bus. This is the processor bus. So this big solid black line, that's a set of wires that almost every component in the LC-3 is connected to, that allows the LC-3 to move data to various components on my computer. You can see I've got my control unit here in this pink box, control unit, which includes predominantly the finite state machine that runs my computer. You can see I've got my processing unit down over here in this pink box, which contains my ALU and some temporary storage. And then below, at the bottom of my diagram, I've got my memory right here, and input and output. Okay, so the LC-3 is absolutely a von Neumann computer, and it's got all 5 of those components. And I think what we're going to do now is kind of dive into this diagram here on the right, and start to illuminate what all these arrows and boxes and stuff are. Okay, so I'm going to jump over to my OneNote here. So I've got the same diagram here on this page here with just a bunch of ink annotations I'm going to walk you through. And so let's start with the processing unit. Okay. In orange here, I've got highlighted my registers, which are my temporary storage. In the LC-3, there are 8 registers. Okay, 8 registers, each 16 bits wide, because the instructions, the pieces of data that are operated on by the LC-3, they're 16 bits wide. So I've got 8 places I can store those. I can store some temporary pieces of data. This set of registers has a couple of signals that kind of control it. So I've got DR, SR1, SR2. These are destination register, source register 1, and source register 2. So these, source register 1 sort of controls which of the 8 registers is being spit out on this port. SR2 kind of controls which of the 8 registers is being spit out on this port. DR controls what is coming in from the processor bus to the registers. And then I've got a signal here coming from my control unit, LD.reg, which is sort of short for load register. This is a signal from my control unit that controls whether or not the value on this signal is stored at the destination register or if it's not. Let's see, I'll point something out in a sec. Okay, so if we scroll down here to my processing unit, I've got my values effectively are coming down here to my ALU, my arithmetic logic unit. SR1 comes straight in. SR2 goes through a little multiplexer. So it looks like I've got the option in this computer to kind of select what's my second operand that goes to my ALU. It could come directly from my register, or if I follow these lines back here, I can see that I've got a portion of my IR, if you recall, that's my instruction register. So a portion of my instruction could specify, it looks like, a literal value that goes to my ALU as the second operand instead of just a register. And looks like there's a bit in there that controls, whether it's a literal value or the register that is that second operand. The value, if it's coming from my instruction, goes through this box here, SEXT, which stands for sign extension. So I've got 5 bits potentially that specify a number. Those 5 bits get sign extended all the way out to 16 bits so that I can do math on the 16-bit wide numbers that are in my LC-3. The ALU, if you take a look at the textbook, can do basically 4 things. I can add 2 numbers. I can perform the logical ANDing of 2 numbers. I can negate a number, and there's one other one that we'll look at a little later. And so what that means is that my control unit has to specify a 2-bit signal to the ALU for which instruction, which operation we're trying to perform. The ALU will do that. It will spit out the result, and then the ALU is connected back to the processor bus to put that result somewhere. But you may recall from the E360 that when I've got a lot of components all talking on the same bus, I need to be able to control which one's actually driving the wire high or low at any given point in time. If the ALU, for instance, were trying to talk to the processor, on the processing bus, at the same time maybe memory was trying to talk to the processor bus, I would have contention. So what I've got down here in blue is something called a tri-state buffer. This is a device that will either allow the ALU result to pass through and to drive the processor bus high or low, or it will float, meaning it will sort of have this kind of middle value that lets another device pull the processor bus high or low. So you'll see this all over the LC3. Anytime I've got a device that is potentially talking to or putting data on the processor bus, it has to be gated with this tri-state buffer. So I've got another control signal here called gate ALU coming from my control unit that is turning this tri-state buffer on and off, that either allowing my ALU to sort of talk to the processor bus or letting it float. Okay, so that's my processing unit. Let's look down at the memory unit now. The memory in the LC3 can support up to 2 to the 16th locations, so that's a little over 65,000 different memory locations. Each of them are 16 bits wide. Again, 16 bits is sort of the chunk of data that we're going to operate on in our computer. You can see here I've got a memory address register, MAR, connected that gets data potentially from the processor bus and sets the address for memory. And whether or not this register loads a value is controlled by this signal here. On the other side of memory, I have MDR, my data register, that performs two functions alternately based on whether I'm reading or writing from memory. If I'm reading from memory, then MDR will get the value out of memory that's we're trying to read. And if we are writing to memory, then MDR holds the value that is going to get sent into the memory. And here's how this works. So let's say I'm trying to read a value from memory. Okay, step 1 is going to be to put the address of the thing I want to read into the memory address register. That takes 1 clock cycle. Step 2 is to let the memory put that value here on this signal. To do that, I have to set memory enable equal to 1. So that tells the memory unit that I'm trying to access it. I'm doing a memory operation. And I'm going to set r.w to 0. That tells the memory unit I'm trying to perform a read. So that tells the memory that it's not being written to. What it needs to do is access this address and place it on this wire here. That should take a minimum of 1 clock cycle. So 1 clock cycle later, the value at whatever address is in here is on this line. So the last thing I'm going to do in my 3rd clock cycle is I take that value and I load it into the memory data register by asserting this signal here, load.mdr. Okay. If I'm going to perform a write to the memory device, step 1 is to still load the memory address register with the place where I want to store this value. Step 2 is to load the memory data register with the value that I want to write to memory. Finally, step 3 is going to be to set these control signals. So again, I'm going to set memory enable to 1 to say, hey, I'm doing a memory operation. I'm going to set r.w to 1 to tell memory that we're trying to perform a write. And then based on those two control signals on that third clock cycle, memory will then read the value that's on this line here, which is the piece of data I'm trying to write, and it'll store it in whatever address I had loaded into my memory address register. Okay, so effectively 3 clock cycles anytime I'm trying to read or write to memory in order to sort of set up these registers correctly. Now, I mentioned that accessing memory takes at least 1 clock cycle. We'll learn later that accessing memory may take dozens or hundreds of clock cycles. So one signal that the memory provides to the control unit is called R, which is short for ready. So if, for instance, we're reading from memory, we've loaded something into the memory address register, we've set our control signals so that we're telling the memory that it's going to read a value. It might be a few dozen clock cycles before this value is actually present on this wire here and able to be loaded into the memory data register. So during that time, what the memory is going to do is set this value R equal to 0 to tell the control unit, hey, we're still thinking the electronics are working, we're trying to get this value out of memory. And only when that value is present does R get set to 1 to indicate to the control unit, hey, okay, the value is ready, we can move on with the processing. The last part of this little subcircuit here I'll mention is gate MDR. So again, the data register, if we're reading a value from memory, we're eventually going to take this value in the data register and sort of send it somewhere into the processor. And so since it might potentially talk or place data on the processor bus, we have to put a tri-state buffer here to kind of gate that signal. Okay, off to the right you see our inputs and our outputs. We're going to spend a lot of time talking about these in Unit 3, so I won't belabor these two items at this point. I'll just mention that the textbook kind of says that we've got sort of a simplified input and output. We're going to pretend we've got a keyboard and a display. Both of them talk ASCII. So we're going to, in some way, we're going to be able to sort of read ASCII characters from the keyboard and write ASCII characters to the display. And you can see kind of briefly that those two units are either, the keyboard is either talking onto the processor bus or the display is reading from the processor bus, and we'll talk a lot more about that in Unit 3. Okay, so the last thing we want to talk about now is our control unit, which is this big chunk in kind of the upper left. We've seen places all over the processor so far where the control unit is sending a signal to control my computer, which we kind of knew intuitively when we were talking about the von Neumann diagram. So we got various load register signals, the ALU operation, memory enable stuff that are coming from this control unit. The heart and soul of the control unit is right here. This is a big finite state machine that performs the instruction cycle over and over again. By that I mean it's able to pull an instruction out of memory, complete that instruction, and start all over again. And this device is configured in such a way that we can write instructions to do some very complex programs, which we'll get into in a future lesson. You'll notice here that I've got really one spot where this clock signal that sort of is the heartbeat of my computer, it comes in, and that just goes directly to my finite state machine to sort of control the clock cycles on this processor. I've got a couple more inputs to this device. One is the instruction coming from my instruction register. The R signal that I mentioned previously is coming from memory to let our processor know when the memory value is present. And I've got this this thing down here with the letters NZP. This is a register. And NZP stand for negative, zero, positive. So this is a register that's set from some logic and connected to the processor bus, which will turn these signals. These are 1-bit signals high if the value on the processor bus is negative or 0 or positive. And so the processor uses these values to potentially change how it's running the program. We'll look at a little more later exactly kind of how these are set, and the processor is able to do that. The last big piece to this control unit that I haven't mentioned yet is up here. This is my PC, my program counter. So this is again the register that holds where in memory I'm trying to execute my program, and you'll notice that my PC, my program counter, is fed by this multiplexer, which can be set with a couple of different values. Nominally, the output of my program counter goes through a small adder to be incremented by 1, and then it comes around to this entry to my PC mux. So nominally this flow around kind of the right hand side here is represents my program counter incrementing by 1, and the way that my computer sort of starts from one instruction and goes to the next, and then the one after that. But at least one of the value that I can set here to my my program counter comes from this wire here, coming from an adder, where it looks like I am adding the value of the program counter to a sign extended value coming from my instruction register. So even though we don't know quite what this is being used yet for, I just want to point out that part of the things that make a computer is the fact that not only it can kind of execute instructions one at a time, and it can do this useful stuff in each instruction, but that it can change the flow of execution based on some parameters. So you're at this point probably familiar with a higher level programming language like Python, where you can sort of encode in Python the ability to run loops and conditionals. And this is effectively how we're able to do that in hardware. We've got our program counter that controls this thing, which we can sort of selectively choose whether or not it gets incremented or it gets set to some totally new value based on the instruction. So this is kind of like the heart of how we're able to make this a full kind of Turing computer. The PC does talk on the bus, so it's got a little tri-state buffer here and a control signal to gate whether or not it's allowed to drive the processor bus. And then the last part of this diagram here is something called the MAR mux, M-A-R mux, which MAR is the same MAR as for my memory address register. So this is a multiplexer which is used to set where my address is coming from that I'm talking to memory. It looks like it comes from this same adder, so potentially I've got the same kind of circuitry where I'm taking the program counter and adding to it some value from my instruction to set what value I'm getting out of memory, and then there's at least one other spot where I might want to sort of change where I'm getting my address that I'm trying to access in memory. We'll look at that in a future lesson. Okay. Yeah, so hopefully at this point this diagram makes a lot more sense. Again, at its heart, it's this the von Neumann diagram, and there are just a couple of kind of control signals that come out of the finite this control unit that allow the processing unit to do to choose different parts of the temporary file to register, this temporary registers to be able to operate on, and which operation it does, and whether we're doing a read or write from memory. Okay, based on this, and I've kind of hinted at it, we can identify that we can sort of get a preview as to what types of things our computer is capable of, what sorts of instructions we can expect to see in the future. So I sort of mentioned when we were talking about the processing unit that it looks like there's something in our instruction register that can potentially we can use as a literal value to be used in an ALU operation, and it's this bit potentially in bit position 5 that controls whether or not my second operand is this literal value or if it's coming from the register. So we already know my instructions, they're going to be 16 bits wide because that's the kind of that's the kind of length of data that my computer operates on, and at least for one of them, the 5 bits at the lower end are going to go to potentially to my ALU, and this little bit in the 5th position is going to control whether or not that happens. When we were talking about updating the program counter, it looked like there was this 9-bit signal coming from my instruction that is potentially going to either the MAR-MUX or the PC-MUX and potentially sort of changing the flow of my execution or changing where in memory I'm accessing information. So I can expect to see an instruction that starts to have this format. I mentioned the ALU, can do 3 things: add, and not, plus one more, because we've got 2 bits here that can kind of control this potentially. So at a minimum, we're going to have 3 operate instructions. These 3, add and not, are going to show up somewhere in our instruction set. And then also kind of looking at the NZP register, we know that these are signals that go to the finite state machine, the control unit, that potentially affect its behavior. So I've got, I don't know where it is in this instruction that's kind of encoded, but I can already kind of start to assume that, or anticipate that I'm going to have an instruction that changes the processor based on whether or not the value here was -0 or positive. So this is just sort of a preview of what's to come. I would imagine some of you can already kind of start to see what type of instructions are going to come next. That'll be in a future lesson. I just want to sort of point out, kind of the marriage between these two, that the parts of our data path that we can already kind of understand it's just electrically controlling this thing already kind of hint at what instructions this computer is capable of. All right, folks, that's all I got. I'll see you next time.